this question, there are slightly different approaches you can take with working out the velocities. So you can take into account the angles as well if you wish, but I did this by keeping the components separate, which is the way I'm going to show you. So they've already got a diagram for us here. I'm just going to give my new velocities some letters, and then there's some information. The floor and the walls are smooth, so we're going to have no problems there with friction. We've got all the rest of the information on. Then we've got the coefficient of restitution. So between AB, it's 1 over root 3, and then between BC, square root of 2 over 5. And they want us to show that the final kinetic energy is 35% of the initial kinetic energy. Right, so I'm going to write down what I've got first. I know my initial kinetic energy is a half mu squared, because that's my initial speed there. Right, we've got two impacts, so we're going to look at them both. So first impact with the first wall. Right, first of all I'm going to look parallel to the wall, and what I'm going to do here is I'm going to split my velocity into two. So velocity in the x direction, and I'm going to call that velocity in the y direction. So parallel to the wall, there is no change in the speed in that direction. So looking parallel to the wall, it came in there with a speed u cos 60 degrees, and cos 60 is a half, so there's going to be no change in that direction, okay, in the velocity along that way. Looking perpendicular to the wall, this is where the coefficient of restitution plays a part. So our value of E is going to be equal to our speed of separation, which I've just called Vy, over our speed of approach, which is going to be u sine 60. If you rearrange that, you can find out that Vy is a half u. So that actually means now this angle here, if you wanted to work it out for any reason, is 45 degrees. And, right, so now we've got our particle travelling. It's then going to hit the other wall. Again, I'm going to split this into two components. So we're going to have going parallel to the wall, and we're going to go going perpendicular to the wall. Okay. Right, so looking this time, remember now, parallel to the wall is that way, so there's going to be no change in this direction, so that means Wy is going to be a half u. I'm now going to look perpendicular to the wall, so our coefficient of restitution is the square root of 2 over 5. In that direction I've called my speed Wx, and again speed of approach was u over 2. So we can rearrange that to get that Wx is u over the square root of 10. Okay, so now I know my two components of my speed after both impacts, which means I can combine these to find out the magnitude of velocity or the speed in this direction. So as I've now got these two components and I want to work out its magnitude, we're using Pythagoras. So the magnitude of v squared is going to be, we've got a half u squared plus u over root 10 squared. And if you work that out, you get 7 over 20 u squared. So this is now my final speed that I can use to get the kinetic energy. Okay, this is why I left it as v squared and I didn't bother square rooting it, because obviously for kinetic energy I want a half mv squared. Oh, actually that should be a w really, that's what I called it. Right, so that's my final kinetic energy. So what did they want? We wanted the fraction left. So the fraction left is going to be my final kinetic energy, which if you work it out is 7 over 40 mu squared, divided by my initial kinetic energy, all the way up here, which was a half mu squared. Obviously these are going to cancel out, and that's going to give me 14 over 40, which is 0.35, and 0.35 is 35% kinetic energy left as required to be shown. Okay, so that's all the kind of long bit. Okay, in reality, of course, the floor and the walls might not be smooth. It's very difficult to get something that's perfectly smooth. So what's going to happen? What effect will the model have had on the calculation of the percentage energy remaining? So we got 35%. So what's going to happen? Well, if there's friction, so they're not rough, then what's going to happen is energy is going to be lost. There'll be some work done, so the final speed will be slower, because you had some resistance, so our final speed will be slower. So if our final speed's slower, there's going to be less kinetic energy left than model predicts. So it will actually be model percentage is too large. So anything that explains that the model has predicted too high.